Okay, thank you. Thank you, Belgian. So welcome to the CHAI seminar today. We are very happy to host Arthur Gretton. So Arthur is a professor with Gatsby Computational Neuroscience Unit at UCL, director of the Center of Computational Statistics and Machine Learning, also at UCL, and also a research scientist at Google DeepMind. Has a degree in physics and system engineering from the Australian National University and a PhD with Microsoft Research and the Signal Processing and Communication Laboratory at the University of Cambridge. And he previously worked at the MPI for Biological Cybernetics and at Machine Learning Department at Carnegie Mellon University at the CMU. So Arthur's research is very relevant to us as a hub because specifically it's about causal inference. So it's causal inference and representation learning, design and training of generative models, and the non-parametric hypothesis testing. Of course, so Arthur is a very well-known person and very active in the community. So he has been associate editor for IEEE Transactions on Pattern Analysis and Machine Intelligence, and action editor for JMLR, RHR for NeurIPS, a senior RHR for NeurIPS, then an RHR for ICML, and then a senior RHR also for ICML, etc., and gave a number of tutorials, workshops, and keynote presentations in a variety of conferences. So welcome, Arthur, and the floor is yours. Thank you for making the time.
Yeah, so thank you, Hannah. And I'm very happy to be speaking to this hub. I know there is I think some time allocated for questions. I'm actually quite happy to have questions during the talk. So if anyone wants to sort of raise their hand, I'm going to pause for questions. And it's kind of nice then because, you'll have the questions close to the time where things become confusing, which will hopefully add clarity. Great. So I'm going to be talking about causal effect estimation with context and confounders. I'm going to begin by giving just a simple example, partly to show notation and partly to sort of give people a sense of the kinds of problems that we're going to be addressing. So here's a very simple example. I hope you can see my mouse. So in this example, this is a sort of hospital setting. And in this toy illustration, there is a disease being treated. The disease has two levels of severity. It can be either mild or severe. So that's this X here. Now, doctors observing the illness will then decide on a course of treatment. So that's A. And in this toy example, there are two mechanisms of treatment. One is pills, one is surgery. So pills more likely when the form of the disease is mild, and surgery when it's severe. Then following that course of treatment and the severity of the disease, you get an outcome, which is that the patient is cured or not. Now, we can observe the historical hospital data from this process, and we get the equations at the bottom of the slide here. Chance of being cured given that pills were assigned is 0.85. Chance of being cured given surgery was 0.72. Now, where do these numbers come from? Well, they come from the formula up the top of the slide, and it's worth looking a little bit in detail at this formula. So given that we've observed that pills were assigned, this actually tells us something about the severity of the disease. And so if pills were assigned, it's more likely severity was mild and less likely that it was severe. Okay, and so the chance of being cured given pills were assigned is like chance of being cured given treatment, given severity, but then we give more weight to the mild form and less weight to the severe form because we observed that pills were assigned. Conversely, let's say that surgery was assigned, then we give more weight to the severe form, less weight to the mild form, because given surgery was assigned, it's more likely that a severe form was present. Okay, so this is how we get these numbers. So now let's say that we're a hospital administrator and we see these numbers and we say, well, pills were cheap, pills work better, everyone gets pills at this point. Okay, so now we're performing an intervention on the system. Okay, I'm going to show the intervention using this graphical notation here. So an intervention is this node with a double boundary on it. Okay, and this node you can see is disconnected from the severity of the disease. So the A is the historical variable. This is what doctors did in the past, but the intervention, which is what doctors, which is what the hospital administrator is doing now, is shown down here. And this A is disconnected from the X because everybody gets pills according to this new scheme. And then the y under this intervention, I'm writing as y superscript a. So this is y under the intervention that everyone gets pills. Okay. And then, under this intervention, which I'm going to express here, so what is the chance of being cured under the intervention that everyone gets pills? Well, it's actually quite a bit lower. Chance of being cured under intervention surgery is a little bit higher. So, what's gone wrong? So this is called Simpson's paradox, but it's not a paradox at all. What's going on here is that, the intervention decouples the A from the X. And so what we've got here is the chance of being cured given A and X, but now everyone gets pills. So we just average this over our population, which incorporates both severe and mild forms of the illness. And so this explains the distinction between the numbers that we get. So I see there's a hand raised by MC. Is there a question?
Hi, Arthur. Thank you. So just a quick query. So, if the intervention is that everyone is taking the pills, the medication, then how do you get the probability of being cured given the surgery if no one is taking the surgery, or is
Right. So that's actually leading to an interesting discussion that will come a little bit later, which is that, given observational data, how do you then compute interventional data? Now, one of the assumptions you need to make is that it's basically called overlap. And it's saying that you need to have observed instances of all of the things you're going to make predictions on. So if I've never seen what happens when you give surgery to someone with a mild form, then I cannot make this prediction. And so this reasoning, the reasoning is valid, but from the data I've observed, I will not be able to conclude anything about the intervention. So this is called the overlap assumption. We need to make that assumption. If we don't make that assumption, then we can we have to make some very strong modeling assumptions instead, which is we sort of take the trends on what we observe and we sort of extrapolate them to things we haven't seen and cross our fingers and hope. That is still a valid research direction, but it's not what I'll talk about in this talk. Okay. So hopefully now we see the distinction between observation and intervention. I'm going to now give the outline of what we're going to discuss on this talk. So I'm going to first of all describe how to compute an average causal effect from observed data. So basically from this observed data, I'm going to basically learn or give an estimate of this interventional result here. So, from the historical observations of the hospital data, I'm going to compute what would happen if we made the intervention that everyone gets pills. Okay. Now, this is not necessarily a very interesting intervention, right? Because everyone, who's going to do that, right? And so what I'm going to spend a bit more time on is a much more scientifically interesting question, which is the conditional average causal effect. So this would be something like, of the patients who have high blood pressure, what would happen if we intervene to give them blood pressure medication? So it's sort of saying, well, we're going to give this intervention on a population where we've conditioned on particular traits. Now, this involves some subtlety, and we're going to get to that as we go through the talk. But this is, I would claim, the more interesting question to answer scientifically, because this is the kind of question that a practitioner would want to know. Now, when we've looked at the causal effect estimation, it's been very key to have observed the distribution over these covariates here. So this distribution over X, because I need to average over this distribution in order to compute my average causal effect. And this will also be true of my conditional average causal effect. So a question then might arise, what if there is some information that the doctors were using to make their decision, but that they have not recorded? Okay, so that's some hidden information in the historical data, which exists, but we don't have any record of it. What do we do? Okay, so the short answer to that question is, if that's all that I tell you, then there's nothing you can do. But with a bit of extra information, with some additional side information, it becomes possible to recover the cause effect. I'm going to speak about two different ways to do that. One is called instrumental variables, and I'll spend most of my time on that. There's a second mechanism called proxy variables. I'm just going to briefly mention that. And if you want to know more, there are some other talks online which go into that in way more detail. Okay, now, causal effect estimation is a very old discipline. It's been used in epidemiology and econometrics and in many, many fields for many, many years. What's new and interesting in this talk? What we're going to be doing is addressing the case where the treatment covariates and all of the side information are very multivariate, complicated, high-dimensional. So, treatment in traditional causal effect estimation literature is usually something like I do it or I don't. So I give a pill or I don't give a pill. But what if treatment is the design of a radiotherapy regime, or treatment is a web ad with like text and images, right? This is very complicated high-dimensional treatment, but we might still be interested in finding the causal effect of particular, medical treatment regimes or web ads or other high-dimensional objects. Likewise, the information we know about our users might be very high-dimensional, very complicated, and we need to be able to deal with that. Okay, how are we going to deal with these high-dimensional complicated objects? We're going to be using features of these things. There are two kinds of features we'll use, either kernel features or adaptive neural net features. And I'm going to talk a lot more about what these are and how they work. Okay, so that is the outline. So now let's get to the material. So lucky for everyone here, this is a very simple talk because it only has one model and it only has one learning algorithm for that model. Okay, so basically, our model for everything we do in this talk is that any function that we want to estimate is a linear combination of features, a sum of features. Okay, so my gamma at x is a linear combination of features of x. I'm using two different forms of notation here.
You are muted. You are muted.
Oh, hello. How long have I been muted for? Recently or?
Just recently, just a few seconds.
Okay, that's interesting. Okay, I did not mute myself, but if it happens again, obviously tell me and I will unmute. Okay. Good. Okay, so all learned functions are linear combination of features. Basically, there are two kinds of features. One is finite dictionary of adaptive neural net features. Okay, so these dictionaries, there's only finitely many features, but these features are learned from data. Okay, the second form is infinite dictionaries of fixed features. Okay, so you fix your features, but there may be infinitely many of them. So you can think of this, for instances, like a Fourier basis, something of that nature, where there's infinitely many features. So it's a very rich dictionary, but you don't adapt those features to your data. Okay, so this is our single modeling assumption that applies throughout the talk. You only need to remember one model. It's this model. All right. Now we want to fit that model. And there's only one algorithm we're going to use to fit the model, and that's ridge regression. Okay, so one model and one way to fit it. Here is the ridge regression formula. So basically, when you're predicting y from x, I have a linear combination of features of x, as I said before. In this diagram, these are neural net features. Okay, now ridge regression uses a square loss. So the error between y and my prediction is the squared error. And I've got this additional ridge term here, which is in some instances a smoothness constraint and in other instances a numerical constraint. But this is something that we're going to use to stabilize our solution in the neural net case and to smooth our solution in the infinite feature case. Okay, so here is just a diagram illustrating this point. So I've got my x's, I find a dictionary of features of those x's, and then I get a linear combination of those features to get my outcome. Okay. So I have two things to fit here. I have a gamma to fit, my final layer, and I have a theta to fit, the theta being the parameters of the neural net that brings me to this dictionary of phi features. Now, I'm going to fit these separately, which is a little bit unusual, and you're going to see why as we get through the talk, but for now, just believe that I'm doing it, okay? I have in closed form, given the theta, I have a gamma in closed form, okay? So what is gamma in closed form for a given theta? Well, it's the cross covariance of my y and my features of x, okay? So cross covariance of y and my features of x times the covariance of my features of x plus lambda inverse, right? So covariance of my features of x plus lambda inverse, okay? So given theta, I have that in closed form. And then what I'm going to do is basically say, look, because I've got gamma in closed form for that theta, I only need to solve for theta. So I put this gamma in, I backprop through, and this is how I get my theta. So I don't explicitly need gamma solved in this instance. Okay, it's a little bit more complicated than that. So please look at this reference down below, and in particular, you may want to sort of have, theta, which is sort of evolving according to a Kalman filter, depending on your current mini batch, but that's in this paper. For now, the main takeaway is that you don't need to worry about your linear final layer. You only need to update your theta features. So that being the case, why am I doing this? Why am I making this distinction between linear final layer and features? I'm not going to tell you yet, but later on in the talk, I will get to that. I just saw the question, is it a kind of EM? I wouldn't necessarily say that, in the sense that, like, I usually sort of think of EM as being something where you sort of estimate values of some latent variables or something of that nature. So I would maybe put this more in the way of coordinate ascent. That's how I would sort of understand it. So I'm sort of doing coordinate ascent on my gamma and then on my theta. Yeah. Okay. Now, what if I've got infinite feature dictionaries? Well, if I've got infinite feature dictionaries, then I would have to write an infinity by infinity matrix here. So that's not great. So I need another way of solving my solution when I've got infinite feature dictionaries. So I've got, in one sense, a simpler problem because I don't need to update these features here, these phi. But on the other hand, I've got an infinitely long gamma vector here. So that's a bit of a problem. So what do I do? Well, this is what the solution would look like, but this is an infinity by infinity matrix, as I've mentioned. But as it turns out, there's an equivalent way of writing this solution that only relies on dot products between these infinite feature dictionaries. And these dot products, in certain instances, we have in closed form. Okay, so this is the equivalent formulation of this. So this is called kernel ridge regression. And what you can see here is that the solution is now written as a weighted sum of my y's, where these weights are given in terms of this expression here, where you can see that this expression here is a function of this matrix of dot products of features between my training xi's. So basically, this is a dot product between features of xi and xj. And then there's vector here, which is a dot product between all of my features of xi and the x at which I'm making my new evaluation. Okay, so if you've seen kernel ridge regression before, you probably haven't seen it looking quite like this. So this weighted combination of y's. I've written it like this because this is going to make later parts in the talk much clearer. So again, I'm doing some foreshadowing here and alerting you to this rather unusual form of the solution. Okay, any questions or any further questions so far? Okay, so we're doing causal effect estimation using feature dictionaries. Either we're using finite dictionaries of features or we're using infinite feature dictionaries. We've published on both topics. So for the case of infinite feature dictionaries, we have a biometrica paper. For neural net adaptive features, we have an iClear paper. Code for both is on this URL, so you don't have to implement it yourself. I'm going to focus for this part of the talk on the kernel features because in some respects, it's a little bit simpler, namely that we don't have to worry about learning our features, but we're going to get to the adaptive features in the second part of the talk. All right. So here is our average causal effect. We've got the chance of being cured given the treatment, given the severity, and we average that over our population. Okay. So this has been known as the dose response curve when my treatment's continuous valued. Now here we're going to make some assumptions. Okay. The first assumption we're going to make is called the stable unit treatment value assumption, no interference. So what that means is that the pill that I take doesn't cure the person sitting next to me. Okay, so in the case of medicine, I think that's a reasonable assumption. In certain other contexts, like advertising, maybe it's not as accurate, right? Because if advertising affects me, then I tell my friends what a great product this is, and so there is some spillover. We're going to assume for this talk that this doesn't occur. This assumption here, which is called conditional exchangeability, what that's saying is that basically, like, the only thing that historically determines, influences both A and Y is this X here that we observe. So there's no additional hidden variable to one side, which is also influencing A and Y, right? Everything that we need in order to see historically how A and Y were confounded is in this X variable here, okay? In the second half of the talk, we'll get to the stage where this X isn't seen, but for now we assume that it is. Okay, then overlap, this is the one that I talked about before. I cannot draw any conclusions about things I've never seen. So in the data that I gather, like the observational data, I need to have observed instances of everything that I'm going to make predictions on. So as I mentioned before, like if I want to make the causal prediction of what happens when I give the surgery intervention to people, which might include people with a mild form, then in my training data, I must at some point have given surgery to people with the mild form. If I haven't seen what happens when I do that, then I can't make predictions about it. Okay, so I'm not making predictions about things I've never seen. That's very important. Okay. So I'm going to illustrate this method with a famous data set, which is the US Job Corps data set. So this is a job training program for disadvantaged youths. In this case, A is the number of hours that the individuals spend in the program, Y is the outcome, so the chance that they're going to be employed, and then X is everything we know about the individuals. So we know, age, education level, marital status, and so on and so forth. Okay, so that is the setting. Now, first of all, you will notice that I'm predicting Y not from one thing, but from two things, from A and from X, right? So I'm predicting my outcome, both by the number of hours that the individuals will spend in the program, and also from everything we know about them. Okay. Now, I have only one algorithm in this talk, only one model in this talk, which is I have a linear combination of features. But in this case, I have two features. Okay. Or rather, I have two inputs, and I need features of this pair of inputs. So the way that I'm going to define a feature of a pair of inputs, A and X, is that let's say I've got good features of A, and let's say I've got good features of X. Then what I'm going to do is I'm going to make a big long vector of products of pairs of features of A and X. Okay, and I'm going to say that this is going to be my feature of the AX pair. It's going to be this big long vector of products of pairs of features. Notice here that the feature of A might not be the same as the feature of X. So I'm using the argument of the feature to indicate which feature I'm talking about. This is to avoid lots of subscripts and superscripts. All right. A question you might ask is, well, is this a limiting or restrictive assumption? In the case where we're using kernel dictionaries, it's not so limiting. So for example, if I'm using Gaussian kernels, then I have, by this mechanism, a set of functions which are dense in the space of continuous functions on X and A, if I'm on a compact domain. So this is a pretty rich domain to be working in. So I would argue, at least in the kernel case, that we're not giving up too much by doing that. There's also a very important consequence of doing this that we're going to get to when we talk about the conditional average causal effect. And it turns out that this trick is the only trick that we can do in order to make it work. So we're going to get to that shortly. So it's a necessary assumption, but not a limiting one. All right. So let's say that we've made this modeling assumption. Now we need to basically learn this gamma, right? We need to fit this gamma. How do we fit the gamma? Well, there's only one algorithm in the talk. It's ridge regression. So we're going to fit it with ridge regression. You'll notice here the ridge regression solution looks exactly the same as it did in the case where we have just a single input X. The only difference is that here we have the entry-wise product.
Πάνω. Ποιο είναι το email που πρέπει να στείλω τα χαρτιά?
We are being encouraged in a Greek, I guess. Okay. Yeah, so absent a translation. Yeah, so this is basically the solution of ridge regression in this case, where we have here just the entry-wise product of the matrix of kernels on A and on X. Okay. So let's say the computational complexity of this is no greater than it would be in the case where I just had a feature of X. I just have to do this entry-wise product of kernels of A and X, and then I have my answer. So this is not very much more complicated, even though I've used this very rich dictionary of features. Okay, any questions about that? Okay, so now we know. Okay, so yeah, so now we have the solution here. We want our average causal effect, right? This is very easy. So I take my ridge regression solution, I just average it over X, and I'm done. Okay, very simple. And that's all I need to do. I can take an additional step. Because of this bilinear form of my features, I can take the expectation inside the dot product and say, well, this is actually the inner product of this gamma, the linear final layer, my features of A, and the mean of my features of X, the expectation of my features of X. That is equally valid. All right. And I can call this my feature map of my probability, or my mean embedding of my probability. Now, in this instance here, doing this is it's an allowable operation, but it's not an operation that I need to do. Okay, so it doesn't gain or lose me anything. I'm just showing that you can do it because I'm going to be using it in a couple of slides. All right, so this is our average causal effect. And let's say we're computing it from data. So in this case, I want to take the mean of my ridge regression solution over X. Well, this is pretty straightforward. I just take my ridge regression solution, and then I just average it over all of the Xi's in my training set, and I'm done. Okay, so this is my average causal effect. Okay, here are the results on the US12 coordinating set data set, right? And so what we've got here is the number of hours that the individuals are spending in the program, and on the y-axis we've got the chance that they're employed. And here we observe a phenomenon which I tell my students is a form of diminishing returns, where you can imagine here they're master students, then they get a PhD, then a postdoc, then faculty position, and then professor. So like the longer you spend, at some point, the worse things get. What you'll also see here is that we're comparing against a alternative method, which is this double debiased method with continuous treatments. You can sort of see that our solution here is a little bit smoother. I would argue that this inductive bias that you get from the features that we use is a more realistic one, and so that this is perhaps a more realistic representation of what's going on. But yeah, this is our finding. All right. Any questions about this before I go on? Okay. So now let's get to this, I think, much more interesting. Yes?
Hi, Arthur. Sorry to bug you again. So would this average treatment affect, so you're averaging out the starting sort of skill of the user or not?
Right. So
It's only a function of the class hours, right?
Correct. That's right. So what we're averaging over is all of the demographics that we know about our users. So we say sort of on average over this big population of users, what's going to be happening if we increase or decrease the number of hours that they spend in this course. So we're at this point, we're not assigning specific treatments to specific users. That's going to come next. Okay. Great. Okay, so now let's say that we're doing the conditional average causal effect. So in this case, what you can see here is that this context information has now been split into two. So we've got X and V. Going back to the example from the start of the talk, when you're doing some sort of medical treatment scenario, what you might have here is that V is high blood pressure, A is blood pressure medication, and Y is the outcome, that the blood pressure goes down or up. Okay, but given that the patients have high blood pressure, there will be some shift in the distribution over all of their remaining demographics. So let's say they have high blood pressure. Well, it's more likely that the age is between 40 and 65, and less likely that the age is between 10 and 15. Okay, and other things as well might shift, like obesity or diabetes. I mean, there's many potential ways in which the distribution of X is perhaps shifting in response to conditioning on V. Okay, now this double-sided arrow here means that we take no position as to the causal influence of V on X or vice versa. So it could be that V causes X, X causes V. There's a hidden common cause. We don't know. We don't care. We only know that X and V are related in some sense. Okay. And so now what we've got is that, historically, the treatment that the individuals are assigned is going to depend on V, blood pressure, and also all of the other covariates, like age, like obesity, like diabetes, et cetera, and the chance of being cured is going to depend, obviously, on the treatment, but also on the covariates and on the blood pressure here. Okay. So what we're now interested in, yes, the recording is available. Yes, so what we're interested in is now the effect of a particular intervention A, like giving blood pressure medication, conditioned on V having some value, like conditioned on the blood pressure being high. Okay, and this is evidently like a much more interesting question than give everyone in the hospital the same medicine and see what happens, right? So this is now, I think, the more interesting question. There is an additional complication here, right? Because now y is being predicted from a and x and v, right? So it's now being predicted from 3 things rather than 2. But that's fine because we just use the same trick as we did before. And so now we make a feature of a and x and v, which is a big long vector of all products of triples of a, x, v features. Okay, so that's actually not that much harder. Okay, and now here is what we're going to do. Right, we're going to take our ridge regression solution, which is this, gamma given AXV, and we're going to take the conditional expectation of that of x given v. Right? Now, v given v is easy, it's v, right? But what about x given v? Well, that's a little bit tricky, right? Because x given v, what do we do, right? Because x is a very high dimensional variable. It's all of the information we know about our patients. V is their blood pressure. So do we really want to learn a generative model to generate patient data given high blood pressure? That seems to be a tough problem, right? If you did it, right, you could do that, and then you could sample from that model, and then you could use that to take your conditional expectation. But it seems that that's actually solving a very hard problem. All right, we don't want to do that. Instead, we use the trick that I introduced a couple of slides back, which is that I take the conditional expectation inside the dot product. And then we notice that all we need to do is to find the conditional feature mean, so the conditional mean of the features that we care about, given v, and then we plug that in, and then we have our solution. Okay, so now we just have a regression problem to the features we care about in order to find our conditional average treatment effect. Okay, so no sampling, no high dimensional data generation, just a conditional mean of the relevant features, which we get by regression. Okay, so let's see how that is done. So I want a conditional feature mean, right? I want a conditional mean of the features of x given v so that I can plug this in so that I can get my average causal effect. All right. What I'm going to do is I'm going to make a modeling assumption that the conditional mean of my features of x given v can be written as a dictionary of features of v and then a matrix of dimension dx by dv, which hits this vector of features and gives me my conditional expected features of x. Okay. Now, I use the phrase operator here. What does operator mean? Well, it means that maybe these dictionaries of features might be infinitely big. And so this is an infinity by infinity matrix. So this might seem difficult, but we're going to get to that. Okay, so we now need to learn this infinity by infinity matrix. We need to obviously make some assumptions in order to make this problem tractable. So what we're going to say is that my f is in the span of the outer product of features of x and v. So it's sort of saying, look, I'm taking all linear combinations of features of x and v and all limits of such sums of linear combinations of features of x and v. Okay. Equivalently, this matrix might be infinity by infinity, but the sum of the squared singular values is finite. So, okay, it's an infinity by infinity matrix, but the singular values are decaying fast enough that they're square summable. All right. Now, this is a very technical way to express the assumption, and it's very hard to interpret. However, this implies a smoothness assumption, which is actually quite easy to interpret, okay? Which is as follows. Any conditional expectation of features of x given v must be a smooth function of the conditioning variable. That means that if v changes, then conditional expectations of functions of x given v can't change by too much, okay? And you can kind of see intuitively why that means it's learnable, right? Because if I change v a tiny amount and then my conditional expectation of functions of x given v change by a massive amount, then there's no hope, right? I'd never get enough data to learn something like that. So the modeling assumption I'm making is that, like, if I don't change v by too much, then my conditional expectation of functions of x given v should not change by too much. Okay, so I have an f which satisfies a smoothness assumption. I call it a smooth operator. How do I learn this? Well, the only algorithm in this talk is ridge regression, so I'm going to learn it by ridge regression. Okay, I'm using ridge regression to map from features of v to features of x, right? This f is a matrix, which is mapping from d phi v to d phi x. Square loss, because I'm doing ridge regression, and then a ridge term. This thing here is the sum of the squared singular values of f. I can equivalently write that as in finite dimensions, the trace of f transpose f, so the sum of the squared entries of f. So it is exactly the same as the ridge term for the earlier case. It's just now expressed as, in matrix form rather than in vector form. Okay, so this is how we are going to solve for this f, which is going to give us our conditional feature mean, which is going to allow us to compute the average causal effect. But this seems like a ridiculously hard problem, right? Because I'm trying to find an infinity by infinity matrix that maps from one infinite dictionary to another infinite dictionary, subject to a constraint of a sum of squares of infinitely many things being finite, right? This seems like something that is purely of theoretical interest. Turns out not. It turns out that the solution is as easy as the solution is in the scalar case, where you're mapping to a scalar. So my conditional feature mean of x given v, which is this infinity by infinity matrix, can be again written as a linear combination of the output features, okay, these output features of my training data, where the weights are given by the exact same expression as in the scalar case. So under this smoothness assumption, I have a very simple solution, which I can compute in one line. And it looks exactly the same as a scalar case. Another way to interpret this is that I'm kind of doing regression individually to each of these output features. And so I'm using the same coefficients for each of those features, so it's no more complicated than the scalar case. So that's another way to look at it. Any questions about that? Great. Okay, so I have just told you that I can get my conditional feature mean by doing as simple a ridge regression as I could in the scalar case. Now let's go back to the conditional average treatment effect problem, right? I mean my conditional average treatment effect of A, of my intervention A, where I've conditioned on V, okay? So returning to the US Job Corps example, V is now the age. So we're saying conditioned on the age of the individuals taking the course, what is the effect of some number of hours of treatment, okay? Now, we have all of the remaining demographic information in X. So that might include, education level, marital status, anything else that we happen to know about the people taking the program. Now, obviously, V is going to have some bearing on X, right? So if the age V is 16, then X is not going to be PhD. If V is 32, then it's more likely that X is going to be PhD, right? So when I condition on V, the distribution of X given V is going to shift, okay? And so, this is what we're basically correcting for when we use this conditional feature mean of X given V. Okay, here is our average causal effect. Gamma is the ridge regression solution when we're mapping A and V and X to Y. But here we've replaced the features of X with the conditional feature mean of X given V. Okay, so we've substituted that in. So this gamma can be done in a line of code. This can be done in a line of code. So we've now expended 2 lines of code in order to compute our average causal effect. I should also emphasize that we have some theoretical guarantees. So as we see more samples, we're guaranteed that this quantity is going to approach the correct answer under some smoothness assumptions, which I've talked about earlier. So see the paper for details, but that's a guarantee that we've been able to provide. All right, let's look at the result now. So on the x-axis here, we have the number of hours that the individuals are spending in the program. So this is the intervention that we're proposing to make. And then on the y-axis, we have the age, and we're conditioning on the age. So we're saying of the individuals who are 16 years old, 18 years old, 20 years old, and so on, what would happen if we intervened to make them take some number of hours of class, okay? And you can see here, like if I slice at 16, then employment can increase from 28% to at most 36% as we go along this axis. If I slice at 22, employment goes up from 40 to 56%. All right. So if I were now a policymaker and I was trying to assign money to this program, I could use this in order to decide, which demographics to give the funding to in order to get the most bang for my buck. So in order to get like the biggest uplift in effect for the individuals taking the program. Okay, any questions? Great. Okay. I should also emphasize that there are other more complicated questions that you can answer using exactly the same tools. A famous instance is the dynamic treatment effect, where you've got, let's say, a series of covariates. Each covariate then informs a treatment. That treatment then influences the covariates and the next treatment, and then you get an outcome at the end. This is famously the case for diseases that are chronic and so require a sequence of treatments in order to resolve. So the famous case of that was HIV/AIDS, where they were looking at the evolution of that disease in response to a sequence of interventions here. Okay, and in this case, using exactly the tools that I've described, you can look at the effect of intervening on various of these A's on the outcome Y. So there was a Bernoulli paper from last year which talks about how to do that. So I encourage you to look at that. Again, the code is online. Right. What if there is hidden confounding? This is the next question. So we saw how important it was to see the distribution over the X. Now what happens when we don't? Okay, so let's say that our hospital administrator got fired from their job in the hospital, and they're now an airline executive. And their job is to find the effect of ticket price on the number of seats sold for their airplanes. Okay, so I'm going to now propose intervening on price in order to affect the number of seats that I sell. So let's say that we see the following historical data. Okay, so on the x-axis A is the price of the tickets, on the y-axis is the number of seats sold, and you see the following pattern. And so then my airline executive might say, well, I'm doing linear regression, and I notice that as I increase my price, I sell more seats, and so I'm going to just make my price as high as I can, and we're going to get rich. Okay, so what have we done wrong? Well, what we've neglected is the demand factor. So X here is the demand. And in this synthetic example, the demand or the desire for travel, which affects both the price of tickets and the number of seats sold, has three modes. So you can think of this low mode here as the demand in the depth of winter. This high demand is the demand during summer. And then this very high demand, or this sort of medium demand, is summer. And then this high demand is during vacations. Okay, so this has three modes. Now, the demand influences the ticket price according to airline algorithms. So when the airlines anticipate the demand will be high, they're going to raise their ticket prices. Okay, and the demand also influences the number of seats sold. So demand is high, you're going to sell a lot of seats. All right, and so this demand factor is influencing both the ticket prices and the number of seats sold. It's a synthetic example, so I can tell you exactly how this works. Okay, so here is how the demand influences price. So obviously, here is demand for travel, and price is going up when demand goes up. There's this additional z variable, which is Gaussian, and I'm not going to tell you what that is yet, but we're going to return to it. So keep that in your minds. What about seats sold? Well, as ticket price goes up, I'm going to sell fewer seats. But as demand goes up, I'm going to sell more seats. And so this is kind of like the interplay between the level of demand and the price of the tickets on the seats sold. Okay. Knowing that these are the equations, you can now see how that pans out in this diagram here. So you could kind of see this is the low demand regime, this is the medium demand regime, this is the high demand regime. And then within each of these regimes, as I increase my price, I sell fewer tickets. Okay. Is that clear to everyone? Great. Okay. So I could then say, well, look, on average, over all of the level of demand, what is going to happen if I increase my price? Okay, because that's a sensible question to answer here. And so then I take my y given a and x, which is this expression here, then I average it over a p of x, as I've done many times in this talk, and then I get exactly the effect that I would expect to get, which is that as I increase my price, then on average over the levels of demand, I'm going to sell fewer tickets. Great. Okay, that's common sense. But what about when I don't get to see x, right? Can I still find this conclusion even if I don't get to see what x is? Okay, now the way that I do this is, well, there's sort of two ways of doing this. One would be to use a randomized controlled trial. So I go to my airline and I'd say, look, for the next month, I want to set my ticket prices at random and see what happens. And then the airline's going to be like, are you kidding? Of course, we're not going to do that. But what if nature forced you to do a randomized controlled trial, right? And this is actually what's going on here with the price of gasoline. So basically Z is the price of gasoline. And when gasoline gets expensive, then the airlines are forced to raise their ticket prices. And when gasoline gets cheap, well, air travel is a competitive business, so the airlines are going to drop their ticket prices. So it's sort of like nature's randomized control trial, because in our synthetic example here, the price of gasoline and the demand for travel are two independent factors. Okay, so it's sort of this Z has a randomization effect on the A. Okay, and so let's say that we take this equation here and we condition both sides on Z on the instrument, then what we notice here is that conditioned on Z, this thing averages out to 0, the X averages out to 0, and then you recover exactly the relation that you wanted, which is that as you increase your price, you're going to sell fewer tickets. Okay, so here is what this looks like on a plot. Here is the conditional mean of A given Z. Here is the conditional mean of Y given Z. And you see it has exactly the downward sloping trend that you are after. So using this instrument and regressing both sides of the equation on this instrument recovers the causal relation, even though I didn't get to see my X. Okay, so this is an instance of instrumental verbal regression. This is a very widely used technique in econometrics. And indeed, the Nobel Prize in 2021 was awarded to econometricians who are pioneering instrumental verbal techniques in many different settings. The sort of art form and the sort of crux of many of their papers is very careful design of the instrument. So you really want to make sure that you've basically assigned an instrument here which genuinely is independent of these X's, of this sort of hidden factors affecting both the ticket price and the number of seats sold. And so a lot of the work in these papers is to really make sure that you've designed a good instrument to do these sort of like, nature's randomized trials. Okay. So this is just to give an idea of what an instrumental verbal regression is. Now let's formalize this intuition. Okay, so what we've got a factor X which is unobserved. It's influencing both the treatment and the outcome, the A and the Y. We've got an instrument which is influencing A, and we need to make a series of assumptions. So one is, you've noticed, it was very key to the requirement that we made earlier, that the conditional mean of my X given Z is 0. Okay, that is one assumption we need to make. A second assumption is that the instrument actually influences A, right? Because I'm saying that this is nature's randomized controlled trial, but if Z is not randomizing A, then everything is now not working anymore. Okay. This assumption here is very hard to pass. Okay, so I'm saying that Y is independent of Z given A if I clip the two arrows going into A. Okay, so what on earth does that mean? What that means is that effectively we're ruling out a hidden common cause down here, V, which is influencing both Z and Y. Okay, we're ruling that out. Okay, I hope you can see my mouse here. So there's no parent of Z and Y. We're not allowing that. And this is what this assumption excludes. And finally, a modeling assumption, right? So we're going to say that Y is a linear combination of neural net features of A, so we're now moving into neural net land, plus X. Now, this plus is very important. The only way that X can influence Y is by a shift up and down, right? So this has to be true because we want to get rid of it by conditioning on X. If X influenced Y by a mechanism more complicated than shift, then I have no hope, right? These instrumental verbals are not an approach that's going to work. Okay, so if we observed X, this would be our average causal effect. We'd average over X, we'd get the linear combination of gamma and this guy here. That's going to be called our structural function. But of course, we don't get to see X, so we're not allowed to do that. Instead, what we're going to do is condition both sides on Z, and then we're going to notice that this goes away and that the effect of the conditional mean of features of A given Z on Y given Z is given by exactly the relation that we're after. And that will allow us to recover the gamma and these features here. Okay, so this is IV. And this is IV where we've made this sort of neural net assumption on the way that A and Y interact. Okay, so you can do instrumental variables with kernels, you can do instrumental variables with neural nets. The code for both methods is in this repository here. We're going to focus in this talk on the case of neural net features, which is something we published in iClear in 2021. We've got some follow-up papers as well, but this is the one I'm going to focus on here. Okay, so what our goal is now is to map from the conditional feature mean of A given Z to Y given Z. I don't have to explicitly condition on Z here because that sort of happens implicitly by the square loss and this conditioning here. Okay, and there's only one algorithm in the talk, it's ridge regression, so we're going to have a ridge term here. Okay, now we have again a conditional feature mean of features of A given Z. right? How do we do that? Well, we do it exactly as we did in the conditional average treatment effect case, which is that we learn a second regression to get my conditional mean of features of A given Z, which requires me on one hand to get this F matrix as I had before, and also to learn these neural net features of Z. So I'm sort of saying that the dependence of features of A on Z is given by neural net features of Z acted on by this matrix F. Okay, it's a matrix F because I'm mapping to the features on A. Okay, so that's great. So now I use regression to get my features of A given Z. I plug that in here, and then I'm done. Okay, seems simple. A question might be, well, look, okay, I know how to learn these gammas here. I have them in closed form, but how do I learn these thetas, right? Well, surely I just learn these thetas by minimizing the loss here, right? If I minimize the loss with respect to these thetas, I'm going to, learn the thetas. Seems sensible. But the trouble is that the phi A of theta does not appear on its own in this regression. It appears as part of a conditional mean. And this conditional mean has to be learned from this regression here, right? Okay, great. So I learned the conditional mean from this regression here, but oh no, to do this regression here, I need my theta, right? To get this theta, I need to minimize this. To minimize this, I need my regression. To do that regression, I need my theta, and round we go. So we seem to get ourselves in a bit of a pickle. What do? Well, here is where the linear final layers come and help us. Okay, so this linear final layer trick that I mentioned right at the start of the talk is going to save us. Okay, how does that work? Let's look at stage one. Okay, so here is stage one. I'm looking for a matrix F, which maps from neural net features of Z to my features of A given Z. Now, learning F is straightforward, and learning these features here is straightforward, right? So F I get in closed form. Okay, I've got my cross covariance of features of A and Z. I've got my covariance of features of Z with themselves. I have my closed form solution, and I plug that in. And I can then backprop through to get my zeta features here. So I minimize this loss with respect to zeta, and I have my F in closed form. Okay, but what I'm going to do, you'll notice that this is a function not only of my zeta features, but also of my theta features. And I'm going to keep F explicitly a function of theta. So this F matrix, I'm going to sort of keep track of the fact that it's changing when theta changes. Okay, so I can optimize for zeta for a given theta, but I can't optimize this theta, okay? But I keep in my head that this F is a function of theta. Okay, so now I take this F, which is a function of theta, and I go back to my original problem, right? So now I'm going to substitute that in. Here is my F, which is a function of theta. So this expression here is a function of theta. Now I'm going to get gamma in closed form as a function of F, which is a function of theta. And then I'm going to minimize that expression with respect to theta. Okay, why is this magical? This is magical because even as I adjust my theta, this conditional mean here remains correct. So I'm optimizing my theta here, and this conditional feature mean basically keeps track of the conditional expectation and makes sure that it remains correct even as my theta is changing. So this is a trick that you need to do, which requires the linear final layers and which is key to making this thing work. Now, since this was published, there has been further work exploring these themes. And so there's a work here that appeared in NeurIPS 2 years ago, which I encourage you to read, which is sort of a more mathematically principled way of doing what something related to what I've just described. So have a look at that for some more up-to-date work. Okay, so now we have a mechanism which allows us to learn these thetas, the gammas are in closed form, and the zetas, and the Fs are in closed form. So we have all of our solution. There's one sort of final step, which is that we need to alternate between theta and zeta. So like, I've said that F is updated as theta is updated, but zeta might get a bit stale. And so what we're going to do is go back to stage one, update my zeta, then go back to stage two, update my theta. We're going to do alternating minimization until we hit a solution. My lights just came out. Yeah. Okay. So this is what we do, and that's it. That's now how to do instrumental verbal regression using neural net features. Any questions about that? Okay. I just want to very briefly touch on the application. So one application of neural net feature instrumental verbal regression is in Q-value estimation. So basically like estimating discounted future rewards given a policy. It turns out this is an instrumental variable regression problem. I won't go into detail, but we have run the method that I just described on these problems over quite an extensive benchmark. And what we found is that it performs quite well. So it's performing on this particular example on par with a method that's sort of designed explicitly for that specific problem, even though this is quite a generic approach. So I just sort of make you aware that one of the biggest application domains where we actually applied this in practice is in reinforcement learning, where it works very well. So I think we're coming to the end. So I just want to perhaps conclude. So I've mentioned how to do average causal effects and conditional average causal effects using features. I've gone into instrumental verbal regression, which is how you can estimate causal effects even when you don't see the hidden confounding. And I've shown how to do this when my treatments, my covariates, everything is high dimensional, maybe very complicated, using either neural net features or kernel features. Okay. Now, what I deliberately haven't done is to model my hidden variables. So in the instrumental variable case, I haven't tried to model my X. And the only algorithm I've used in this whole talk is ridge regression. So ridge regression is all you need. So I want to, of course, acknowledge the research support. So this is the Gatsby Charitable Foundation, Google DeepMind, and then part of the AI Hub in generative models as well. And I'm happy to take any further questions. So thank you. Any more questions?
Thank you so much, Arthur. I think it was brilliant, and I will make the link available as soon as possible. I think there were lots of people really wanted to join. Some reason, some of them weren't able to, so I will make sure the recording shared immediately. Thank you ever so much.
Sure, yeah. And yeah, I'm happy also, like if anyone's got any follow-up ideas or questions, like, yeah, I'm easy to find online, so you can send me an email. Yeah, cool. All right, well, yeah, thanks again for the invitation. And
Thank you.
It was a lot of fun. So hopefully I'll see you in person as well at some point. Yeah.
Brilliant. Thank you. Same.
Okay, cool. And thanks, Michael, as well. He is giving a message. Cool. All right, then. So I'll sign out.
Bye-bye.
So
Thank
bye.
you.
Yeah.
Bye, everyone.